Hi, this video is the first of a few that are going to be comparing vectors and linked lists. We've studied these data structures in detail. Now we're going to compare and contrast them and try to come up with which one should you actually use. So the goal of this little segment we're doing is so that in practice you can decide between these sequence structures. So we've covered vector, singly linked list, which we abbreviate SLL, and doubly linked list, which we abbreviate DLL. What we'd like to happen is that if you are a software developer coding something or an algorithm designer designing an algorithm, and you need to store some elements in a sequence or list, you need to choose which of these to use, and we'd like you to be able to make a good decision there. This being a scientific enterprise, we use scientific reasoning. We don't just guess or go by habit or something. We go by evidence and analyses that say which is the right decision to make under the circumstances. This is an example of an engineering trade-off. So each of those structures has some specific advantages and disadvantages, which we're going to explore here. And that means that none of them are obsolete. The three that we have here, vector, singly linked list, doubly linked list, each of them has an advantage that means in a certain situation, that's the best one to use. So we still keep them around and we still teach them and talk about them. There's some other data structures that have come and gone that we don't really spend time on that are obsolete, but these three all have a place. So you make that decision based on the circumstances. The engineering trade-off idea is that, if we choose a vector, one thing gets faster, but a different thing gets slower. Same for the other two. And you want to make the choice that matches what you're trying to accomplish, meaning the code you're trying to write or the algorithm you're trying to design. Ultimately, we're going to boil this down to a decision tree. Before we get to that, we have to make some observations about the factors. This video here is going to look at time efficiency. We're also going to look at the space efficiency in the next video. So here is the asymptotic efficiency of these three operations. The whole idea of asymptotic notation, otherwise known as big O, is that says how these operations scale up to large input sizes, and that's the most important factor in terms of the runtime of these data structures. So this table shows the three structures we've covered: vector in the left, singly linked list in the middle, doubly linked list on the right, and the operations that we've studied. And the yellow cells are where there's a significant difference. You can see there's a lot of ties. Big O of 1 is the best efficiency class, and these data structures are tied for the best possible efficiency class in a lot of places: the constructor, size accessor, front and back accessors, and the pushback operation. They're all constant time. The vector is amortized constant time, which is a minor detail, but constant time. There's big differences in these other operations. So let's pick out some observations here. As I was saying, we've got a tie on those operations. Pushback is a tie except for amortization. Vector has the fastest get index and set index operations down on the bottom here. The vector can get or set at a given index in constant time because it just does an array subscript. Singly linked list and doubly linked list need to skip over nodes in a loop in order to get or set an index, so they take linear time. So vector is a clear winner on that operation. However, vector has slow push front and pop front operations. If we look at push front and pop front, vector takes linear time, and that's because the vector is a contiguous array. If you add an element at the front, you have to scoot everything out of the way to make room, and that takes linear time. And similarly, pop front, if you take the first element out of a vector, you have to scoot everything down to kind of close that gap in a loop that takes linear time. The singly linked list and doubly linked list are constant time for adding or removing the front. So vector is a clear loser on pushing and popping the front. And singly linked list has a slow pop back, removing the last element. In that row, vector is constant amortized time, doubly linked list is constant time, singly linked list is the exception, which is linear time and much slower. So those are some trade-offs right there. Another thing we can look at is constant factors. So constant factors are less important than the efficiency classes, but they're a way that we can compare two equal efficiency classes. So if we compare, for example, pushback, all three of them are constant time in terms of big O. They're tied in terms of big O, but we can zoom in and look at smaller differences than big O of 1 versus big O of n and see the constant factor on these. Big O of 1 means a constant function. It's the same amount of time to add to the back regardless of how big the data structure is, but maybe vector is a less amount of time, or maybe it's a more amount of time than the others. So constant factors are kind of a tiebreaker between equal efficiency classes. And a common operation is filling up a vector or linked list or iterating through them. Those are linear operations according to Big O. One major driver of differences in the constant factors are the CPU cache. This is a component of practically all CPU chips. And as an optimization, what they do is when you access a given memory location, this CPU cache will also prefetch the next location over. And that's based on this observation that often in practice, if you look at one memory location, you're very likely to look at the next. You know, if you look at the first element of this array, it's very likely that you're going to do a loop that goes through all of them. So that's an optimization that works in practice. As a consequence, when you have a data structure that arranges the elements in contiguous order, those data structures tend to be faster because of that, because of this caching. Now, a vector does arrange elements in contiguous memory. It stores all of the elements in an array, and part of the definition of how an array works is each element is adjacent to the next in terms of memory addresses. So vectors have what we expect good constant factors. They're faster because of this contiguous shape. Linked lists are not contiguous. The whole idea of a linked list is each element is stored in its own node. That's true for a singly linked list and doubly linked list. And most likely those node objects are not next to each other in memory. They're probably scattered at very different addresses. And so the cache will not be able to prefetch. If you fetch the node containing 7, odds are that the node containing 1 is at a radically different memory location, and the CPU cache will not help speed things up. This tends to be true in practice. I did a quick experiment on my MacBook where I wrote code that added 10 million ints to a data structure, and the vector took approximately 0.9 seconds. The singly linked list took approximately 3.3, so about 3 times slower, and the doubly linked list took about 4.8, so about 4 or 5 times slower than the vector. And this is predicted by the science because the vector is contiguous. It has a big speed up with caching compared to the linked lists. And then it makes sense that the doubly linked list is a little bit slower than the singly linked list. This is driven by the fact that the doubly linked list just has more pointers. So when you add a node to the back of a singly linked list, you only need to update one node pointer. When you add a node to the back of doubly linked list, you need to do more because of the double links. So that extra slowdown of doubly linked list in terms of constant factors is coming from the larger number of pointers. So on this measure, constant factors, vector wins. Vector is fastest. Singly linked list is slower than that. Doubly linked list is a little slower than that. So here are the conclusions we can make based on time efficiency. The first most important factor is the asymptotic efficiency of the operations you actually use, the big O versus big O of n. If you need push front, push back, and pop front to be constant time, then you should use a singly linked list over a vector. If you need those operations and you also need pop back to be constant time, then you need to upgrade to the doubly linked list because that's the only of these 3 data structures that has a constant time pop back. If you certainly need a constant time get index or set index, you've got to go with vector because that's the only data structure that can do that. But if those are not deciding factors, those operations, then you might as well use the vector because the vector has the best constant factors. So in this everyday use case of starting empty, using the pushback operation to fill the data structure with elements and freeing it, the vector is superior. We saw it was about 3 or 4 times faster than the linked lists.